the topic is quite specific, which is design of heat exchanger. Okay, design involve a lot. Okay, design involve first of all we will learn about what heat exchanger is. Okay, the type, the use, and so on. And then the next step will be about design. Design involves two things. The first one is what we call as process design. Process design is, for example, you want to cool, for example, you want to heat an oil from temperature, room temperature 27 to frying temperature 400. Okay, so from room temperature to 400, that is called as process design. That is process design. Basically, that is the process objective. For example, you have an aircon and your evaporator, it is inside the house. So your objective is to evaporate the refrigerant, okay, from a mixture of liquid and vapor, for example, to saturated vapor. All of the liquid is evaporated at constant temperature. So that we call as process design. Okay. Another example is that you have a condenser. Normally in aircon, it is outside of your house. So the aim is, okay, you have a saturated liquid coming in, and then you want to make it, you want to change you want to drop the temperature down, okay, through the expansion in this case, okay, and then you want it to be to reach certain pressure. So whatever the temperature, it will follow. So you want to reach the same pressure. So that's what happened in refrigeration. So basically, what you say that you want from this condition to other condition, we call as process design. Okay, that is normally done by chemical engineers. Chemical engineers, you are energy engineers probably, but most of the time, process design is done by chemical engineers, okay, in industry. So what mechanical engineers, I think you're closer to mechanical engineer to is, you do sizing. So remember, design, there are two things. The first is process design. So this is a process design. And the second one is sizing. Okay, since you are not a process engineer, so most of the aspect I will discuss later on is on sizing. Okay. What it is heat exchanger? So it's the keyword is probably the last two letters. So it's a tool. Okay, it's used to transfer heat from hot fluid to the cold fluid. So this one, okay, this one, what we want is spontaneous. Okay, the process is spontaneous, is from hot fluid to the cold fluid. Okay, in that is normal. It will happen without any work being done. Okay, that is process is spontaneous. It's used a lot in industry. For example, you want to heat a fluid from low temperature to high temperature in the next process. Example is probably, okay, we'll discuss about the power plant. Okay, you want to evaporate water, but before entering the boiler or evaporator, you need to preheat the water. So from, for example, warm water, 60 to close to 100. That is, for example, you want to condense vapor or evaporate liquid, condenser here. You know it in the refrigeration and air conditioning. Evaporation also, you know it in the refrigeration. To recover heat to use elsewhere. For example, you have stack gas, you have a combustion. In the chimney, you still have a hot flue gas. If you want to recover that heat, you can use heat exchanger. Okay. To reject low grade heat, to drive power cycle, and so on. So many, and it's so important. So I want to tell you one story, which is the most important lesson I learned in thermodynamics. So during my PhD, there was invited professor coming to my university, And the professor was really like an expert in thermodynamics. And then he started his talk with these things. He said that, I want to tell you what is the most important in thermodynamics. Okay, thermodynamics. And then he said that, first of all is everything is either in equilibrium or they are approaching equilibrium. Okay, equilibrium means is equal. So approaching equilibrium means, for example, you have a hot air, okay, in one space, and then there's another cool air in another space, and they try to reach equilibrium to having the same temperature through the mixing and so on. Okay, so things are either equilibrium or they are approaching equilibrium. So how to change things? There are only two ways, and it requires two ways. Okay, if you want to change some things, you need to do two things, or four things, if you want to make this classification. Put matter, bring matter, mix it. Okay, that's number one. Or take out the material from it. Okay, you bring in the material and you take out, or you take out material of it. That's the first two. And the second two is that you can bring in heat, you can bring in energy, or you can take out energy from it. Okay, there are these four things. And then if you want to address physical things, you just ask these questions. Okay, so you will know what happened. You will know what happened. I'll give you an example. You want to evaporate water. Say you want it to change the phase from liquid to vapor. What you do is you need to bring in heat. Right. Okay. For example, you want to build a house, you need to bring in material. Okay, that's material to build a house, and energy, basically the work that need to be done. So this principle is inherently happen in every thing when we discuss about changes. Okay, I just want to share that one, and the knowledge of that changed me a lot scientifically, so I can address a lot of things. Okay, I will talk about the second most important thing he said. Okay, let's run. Okay, so from the previous chapter, we learned about refrigeration, and then one of the example slide I use is this one. You look in refrigeration. Actually, we have heat exchanger. Yeah. So the condenser here is basically, it's called condenser because it's changed the phase, the refrigerant from vapor to liquid. But what happened is actually there is a transfer of heat from the refrigerant to the environment, to the air. Okay, so that's why you have it here in condenser. In condenser you have Q out. Okay, so basically this one is heat exchanger. Then you have an evaporator here. Okay, in evaporator, what changing is that you change from 0.4 to 0.1. 0.4 is basically a mixture of 35% of vapor and the balance is liquid. You change it to the all become vapor, saturated vapor. So there's a change of phase of the refrigerant. But to be able to do that, you need to bring in heat, which is the Q evaporation here. So this one is also heat exchanger. Okay, and if you notice, I have this contrasting image. So this is air conditioner on the building in Fuzhou, China. Okay, and then the caption of the report said that there is a prediction of the number of air conditioning unit will rise from 1.6 billion to about 5.6 billion. Okay, by mid-century 2050. A lot of air conditioning, and then we are dealing with a lot of heat exchanger that we are. So all of you see here in this building is basically a condenser, and there each of them is heat exchanger. Okay, and I remember one air conditioning unit consists of at least 2 heat exchanger. The one inside of the house, which is the evaporator, and the one outside the house here is condenser. A lot, yeah. So in case of refrigerator, then we have air cooled heat exchanger. This is happen in the condenser of the aircon placed outside the house. You can have fin tube here. I think this is a air draft, induced drought heat exchanger. I'll go back into much more detail in the next slide about this type. Okay, so what's the application and the type of heat exchanger? So to produce electricity, well, you might say, no, it's not that one. So produce electricity, we use heat exchanger in power generation a lot. Okay, but probably less so here. In building, in subtropical countries, we use heat exchanger in a central heating system. Okay, cooling. In our case, want to cool down the house. Ice making, we use heat exchanger over there. There is a refrigeration, beverage cooling, hydraulic, engine oil cooler, and so on. And this picture basically illustrates something related to the energy audit of the building. Okay, the heat exchanger is used to heat up the house, heating up the swimming pool here. Okay, heat exchanger is used to prepare the hot domestic wastewater, increase the temperature of the floor, to melt the snow. So they are more relevant to the countries in subtropical climate. Okay, when we talk about the heat exchanger, it refers to three broad categories. Okay, number one is called double pipe heat exchanger. Number two, okay, the double pipe heat exchanger is probably lessly used in industry because of well, I think we discussed that one. Then shell and tube we use mostly in process industry. Cross flow is the one used mostly in refrigeration, in thermal comfort. Okay, and then I'll go one by one. Okay, first of all, plate and frame heat exchanger. So it consists of many plates, as you can see from this image. Okay, alternatively, sorry, there is a gasket here in between the plate, so you don't notice it. There is a gasket that separates the plate, and it's very flexible here. High heat transfer coefficient, used at relatively low pressure and temperature, and used for clean fluids. If you want to look into different elements of the plate and frame heat exchanger, you see different part here. But I think this video will give you a better illustration of how it works. Yeah, those are the plates. So it's screwed tightly, and with a lot of thin plate, it will allow us to have a very high heat transfer area. Okay, and that is the cold fluid, okay, coming from the bottom, alternatingly through the plate, and then these are the hot fluid. And this is how the flow look like when both hot fluid and cold fluid flowing. Okay, another thing is that in the corner of the slide, I put some QR code. So if you want to go, some of the material I got it from YouTube. So easy for you to go and exploit more, yeah, explore more about the information. The knowledge of heat exchanger is very well established, so you can find the resource easily from the internet. The part that I'm discussing here is very general. It's really applied, and we really narrow the focus on the design part of the heat exchanger. Okay, so go ahead later on when you have some time. Go look into the resources in the internet. Okay, so the other type is the double pipe heat exchanger. So it's basically the name is explain itself. So you have two pipes. Okay, the first one is the one inside. It is the tubes, and you have a bigger pipe here. So this one. We have this bigger pipe on the outside. The typical size for double pipe heat exchanger is around 0.25 to 200 square meter per unit. Typically, it is built of carbon steel, and normally there are multiple units. Okay, this is very famous. I think it was among the very first time used heat exchanger during the early industrial revolution. It's simple, easy to design compared to the previous previous plate and frame heat exchanger. It's simple and cheap. Okay, the area between the tubes, basically that is the effective area for the heat exchanger, and the system can run either parallel or concurrently. What does that mean? So when, okay, for example here, the general flow of the blue liquid is from left to right, and then the general flow of the red arrow here is from left to right. So when you have this kind of flow configuration, we call it parallel flow heat exchanger. Conversely, you can operate it, for example, here the blue liquid, exactly the same as the one on top. Okay, so the general flow direction is from left to right, but the hot liquid or the red arrows represent in this illustration, it is from right to left. So when the general flow of the fluid is in opposite direction, it's called counterflow heat exchanger. Okay, this is a snapshot of a short video showing the general flow of double pipe heat exchanger. Okay, the problem with double pipe heat exchanger is if you need a very high surface area, it leads to very high investment costs. You see here in the illustration, the shell fluid, I think blue represent the coal, goes from, okay, so see, it goes from, in the opposite direction. You see now you have multiple pass double pipe heat exchanger. So what is multiple pass? So this one, okay, so it's one level, is called one pass. So, okay, the second level is the second pass. The third level is the third pass, the third pass. And the fourth level is the fourth pass. So this is what we call as 4 passes double pipe heat exchanger. You have 4 lines in stack, okay? Because later on you will encountering the same things with another type of heat exchanger. Okay, next, the most common one used in industry, which is shell and tube heat exchanger. I think this image gives a general illustration about how it works. As you can see here, you have tubes and then 2 things, tubes and then shell side. Okay, in the tubes, for example, here you see here the inlet coming from here, the tubes. Okay, and then they have, I don't know what is called here, plenum. Yeah, things. Yeah, the plenum here Okay, so you got the liquid level equalized, and then it's moved through through the interior of the tubes to the outlet here. So that is one of the liquid, and another liquid flowing through the shell side. Okay, for example, here in the illustration, it's come from the top left. Okay, goes through the shell. So and then inside the shell there is this is called as a baffle. So the general movement of the liquid then slightly different. So it's from here, it's not straight, go down and then goes up, down here, up and down here. So that is general flow of the liquid. Okay, so detailed attribute of shell and tube heat exchanger is shown from this image. Okay, and this one called straight tube heat exchanger, and it says two-pass tube side. So what is two-pass tube side? You see, it's the tube starting from the top here. Okay, come in here, tubes, goes to the end, and then bend down. So basically, this is pass number 1, and this is pass number 2. So this is two-pass tube side heat. Shell and tube heat exchanger. Okay, and the general movement you can see from the arrow here. So I can say the liquid come in from this side. So this is the inlet plenum, they call it. Okay, it equalizes the level here so that it flows through the interior of the tubes to the other sides. Okay, mix here, goes down, leveling up again, and then it goes through the pipe to the opposite direction. Here, okay, collected in the outlet plenum and then goes to the tube side. So this is the tube side flow, and you have the shell side fluid here, goes in here. Okay, it is the flow is basically directed by baffle, so it goes down first. Cannot go directly there because it is blocked by the baffle, goes down, and then now there's a baffle here, so it goes up, goes down, goes up, down, and this is the exit of the flow. So shell and tube heat exchanger is very versatile. Okay, it is really the most common things you can find in the industry. It operates with most fluids, clean or dirty. Okay, it can operate at wide temperature and pressure range, easy to maintain and repair, and so on. If you notice, there's a big difference between shell and tube. So the main advantage of shell and tube heat exchanger is that when you have a very large area, and when you require very large area, so we have a very small space. So basically, call it, what's the term? Specific surface area. The packing density. The packing density of shell and tube is much higher than double pipe. Remember, double pipe is basically conceptually the same. So you have a shell side and you have the pipe side, but instead of like this one, it's a combined shell for very long tubes. Okay, in double pipe you have a very long shell and very long tube heat exchanger. Okay, and then it says quite easy to maintain and repair. Okay, so I got a short video here to show how it works. Very nice animation you can find. Okay, and I have here much better illustration of how the flow Okay, so this heat exchanger, it has one pass of shell side. Why I know it is it's starting from shell side. It's starting from here and end up here. Okay, while the tube it has two passes. Yeah, so you get the first passes here to this direction, and then the second passes goes and at the bottom part to the other direction. Okay, so that is basically the general flow of shell and tube heat exchanger. When I learned the heat exchanger, it was very hard to imagine in the past because we don't have fancy and nice video like this 20 years ago. But you are very lucky now. Things are on the fingertips. Yeah. So I really encourage you to go find out resources in YouTube to learn more. Okay, the last type, which is the one that I will put in the exam, is cross-flow heat exchanger. The reason why I will use this one as the one in the exam is because of this is the most relevant to the scope of the work. Okay, so it is two fluids flow at right angles to each other. Cross-flow heat exchanger might be further subdivided into unmixed flow arrangement and mixed flow arrangement. So this is the one that actually used mostly in refrigeration and air conditioning and heat pump. Okay, since we are auditing energy in the residential, so I'm going to use more of this case in these models. Okay, so what did I want to say here? Forget. So you see here that from the previous example, we have an evaporator here. We have an evaporator, and then in this evaporator, we use the air in the house, okay, to evaporate the refrigerant. So basically, we have an air which has no basically general pipelines. It's not in shell side, so it's just the outside fluid. That is the heating fluid. Okay, and then we have the one inside the evaporator, which is the refrigerant. Okay, in another side we have more or less the same, but instead of evaporating, now we are condensing. So basically, in these two heat exchanger, okay, there is a change in phase. Okay, the evaporation is from liquid to vapor, condenser is from vapor to liquid. We can also have the different type of heat exchanger, as I saw in the example. We have the internal heat exchanger here. Okay, this internal heat exchanger, you change the temperature only. Okay, for example here, the refrigerants that at 0.1 to 2.1x. That one, I don't know, increase the temperature. Yeah, you increase the temperature to 20, and then in another side you have 0.3 refrigerants, temperature around 36. Okay, it is, I don't know, it's supposed to be cool down here. Yeah, cool down from, I don't know what temperature is this. This is about 36, and this one 3x is about 10. Yeah, so you got it to cool down. So you see that there are 3 heat exchanger in this configuration. And there are many types of this heat exchanger. So basically, we have a fluid, okay, inside a coil. So this is the fluid in the context of refrigerator. The fluid is the one that inside the coil, okay, coil, and you have the fluid number 2, which is outside. In this case, it is the air, okay. Whether it's a cool, rather cold air inside the house, or slightly warmer air outside the house. Okay, that is the thing. And then in this kind of heat exchanger, we can use water as an example. So you have a water in here so you have a hot water in coming, okay, and then it is in contact with cold air, okay. So you can, and the one goes out is the hot air. So that is a basic example of cross flow heat exchanger. The application for this type of heat exchanger is mostly for air handling unit, fan coil unit, duct work system. This is for big building, air conditioning, evaporator and condenser, trench heater, and so on. So if you look into this application, okay, the module the topic in this module is more suited with this type of heat exchanger. Okay. Okay, this one is with coil. Okay, you have a coil and then you have fins. Basically, fins here is to increase the heat transfer area. I will discuss later on. And we have different type. This called as microchannel heat exchanger. It's the microchannel help to enhance mixing. Okay, enhance contact of the air and the coil. Okay, so you got, for example, here illustration, a refrigerant flow internally. Okay, it is really like a shell type of in the shell and tube heat exchanger. You have this planium, what's called it, planium. Okay, go and then go through the tubes, go to this side, okay, and then drop down, okay, and return back here to the other direction. So it's basically two pass of the tubes and one pass of the cell. Okay, you see the hot air coming from your side to the screen side, to the behind the screen side. Okay, that's it. So got three types of heat exchanger, and we'll be focused more actually on the cross flow heat exchanger, the last part. Okay, next is the calculation. Okay, heat exchanger calculation. So I'll go back to this one later on, but this is the concept. So we have, we call the term U here. Okay, the term U is called overall heat transfer coefficient. Okay, overall heat transfer coefficient. It is a function of, okay. So we can look into U from the inner side, okay, the one that inside the tubes, or we can look at it as the system from the outside of the tubes. Okay, and it is function of, okay, first is convective flow. Okay, it's from bulk liquid. Okay, you have to bring it to the wall. Okay, that's the first step in the heat transfer. Then its K here is conduction through the thin wall of the tubes. Okay, this is the conduction part. Okay, and the next part, okay, the third part is actually the convection part inside. To the outside. So that is the thing. So imagine you have basically this is the wall. Okay. From they call it bulk. Okay, from bulk through to the wall. Okay, this is a H inside. Okay, the function of heat transfer, convective heat transfer. Then through the wall, it's a conduction. So it's you have a K here. And then from this wall to the bulk outside, you have convective heat transfer of the outside. And then you can do exactly the same for the U out. Okay, so Q, let's say here, the Q is same irrespective of which U. Okay, you can use U1, you can use U2, and then the overall heat transfer is the same. Normally, okay, this is normally. Normally, if you are a chemical engineer, or if you learn fundamental of heat transfer, we will have some method to obtain this value. Okay, you will have a method, call it Prandtl number, Reynolds number. It's really a function of what type of liquid, what type of the material used for heat exchanger, the flow, the flow properties, is it laminar or turbulent, and so on. So you'll be able to estimate the U. But in general, based on experience, we have generally this U. Okay, why this table is so important? Okay, imagine I give you problems, and then the problem will require you to solve. For example, I want you to size the heat exchanger. Sizing basically means what will be the overall heat transfer area, so A. But I don't give you U, so you won't be able to solve the problem without knowing the U. So in some cases, you might need to guess. Okay, and then guessing is really depend on this attribute. Okay, when you want to condense the steam, you have more or less this value. When you want to heat the water, okay, but not evaporation, you will have more or less this value. Okay, if you want to heat water with water, you will have more or less this value, and so on and so forth. Okay, so this table is highly important for us as an engineer to be able to do design of heat exchanger. Okay, the second thing is, okay, I remember my story about the professor. So the second thing, professor said that he said this nothing lasts forever. So you can get this U from the estimation, but this U will deteriorate over time. So your heat transfer coefficient will decrease over time. Why? Because nothing lasts forever. So we are dying. Everything is about in the process of breaking down, right? Everything. Okay. Some do it very fast. Some broke down very slow. So the same thing when you design heat exchanger. Okay, there is a thing called as fouling. This is the analogy of us. This is the cancer things of heat exchanger. So what is this? So normally when we design heat exchanger, we say that it is fully clean. Okay, fully clean. Okay, all the time it's clean, but over time, actually, when we use the actual liquid, heating liquid and cooling liquid, there will be a build-up of deposit build-up of deposit. So this deposit will stick on the surface of the heat exchanger. So because of that, you don't have the same overall heat transfer coefficient anymore. So there will be an insulation effect. Okay, it can be from inside, it can also be from the outside. Okay, so when this happens, you have extra resistance from the inside, which is this one. Okay, this called as resistance, falling resistance, and you can also have a falling resistance from the outside layer. Okay, that's the thing. So this gives a theory that why, for example, a chemical plant need an overhaul every year. So basically, they stop it for a few weeks and do all of the cleanings. Okay, restore the performance, clean the heat exchanger, wash out the foulants that stick on the surface of the heat exchanger. So what are those values? Okay, typically the values, if you are dealing with seawater at this given temperature below 50, is around very small, 0.001 meter square Kelvin per watt. Yeah, and then the highest here, I think, is here when you're dealing with fuel oil. Okay, so this one is very important in oil and gas industries, especially when they need to do what you call a fractionation of crude oil. So the first stage of crude oil processing is basically to separate water. That's number one. So to separate the sand particle and to separate gas. So when they have a liquid crude oil, so they fractionate it through the distillation, and in distillation there are many heat exchanger, many. Okay, that's why it's quite important. So next, let's do analysis of heat exchanger. Okay, on the left, you see here I just do it one end, and when we do the analysis here, we do it for double pipe heat exchanger, double pipe one pass heat exchanger. So this one, double pipe single pass heat exchanger. Okay, that's the thing. So H indicate the hot fluid, and C indicates the cold fluids. Okay, so the hot liquid come in, okay, here at temperature of T hot in, and because of the heat is taken out from the stream, it exits the heat exchanger at lower temperature, which is T hot out. Okay, and in doing so, we need to flow certain mass. Okay, so this is a mass flow rate, this one. And then each fluids, they have important properties here, which is the heat capacity. So this is a mass, and this is heat capacity. Okay, and we know that, okay, when we transfer heat, we know the equation is the heat that is transferred. Okay, I'm referring to the hot, so equal to the mass of the hot times Cp of the hot times delta T, which is a T hot in minus T hot out. So that's one. I can look into it. So this is a Q hot. Then I can also say that there is a Q cold. Okay, Q cold is equal to MC. So, sorry, mass of the cold times Cp of the cold times T cold. So which one is higher? T cold out minus T cold in. Okay, this is called, so this is a counterflow heat exchanger. Okay, counterflow heat exchanger. You can also have a parallel flow heat exchanger like the one on the right side. So this is a parallel flow heat exchanger. And it's also the same. So here we have a Q hot, then equal to M hot, Cp hot. Okay, sorry. Okay, T hot in minus T hot out. Okay, and then Q cold here then equal to M cold, Cp Cp cold and Tc out. Salah. This is Tc in and this is Tc out. Tc out minus Tc in. Okay, so it's a Q hot equal to Q cold equal to Q. And then Q equal to U A delta T. Okay, QA delta T. So this is the analysis of heat exchanger. So it's the same, Q cold equal to Q hot equal to Q, but the question is what is the Q here? So what is delta T? Big problem. U here is, we know it's the overall heat transfer coefficient. It's function of a convection heat coefficient, conduction heat coefficient, and another convection heat coefficient, also affected by the fouling. Okay. A is, we know it. It is the total area of heat, total heat transfer area. How about delta T? How about delta T? Delta T, which delta T? Because delta T at this point is different than delta T at this point, different than delta T at this point, different than delta T at this point. Okay, so that's the thing. That's the big question. So how can we find out what is the most ideal delta T that can be used in this calculation? Yeah. Okay, so this is one issue, delta T. Okay, then I will discuss it later on. So the way to address heat exchanger, there are three things. Okay, this one you need to remember. You put it as the algorithm in your mind. So number one, it's called as LMTD, logarithmic mean temperature difference. So that's number one. Number 2 is the corrected LMTD, CLMTD. And number 3 method is the effectiveness NTU method. So there are 3 methods and really depend. Okay, the condition I'll give it now. LMTD is only valid for double pipe heat exchanger. Okay, double pipe heat exchanger. Okay, in double pipe heat exchanger, why? Because in double pipe heat exchanger, we can define what is the TM. What is the TM? Okay, the delta TM here is called, okay, LMTD, log mean temperature difference. We can define it for only for the double pipe. So when we have different type of heat exchanger, we have no idea of how to do it. That's why, okay, that's why number 2 and number 3 is basically somehow empirical approach to do number 1. Okay, and then I will go through that one by one later on. Okay, so what is the logarithmic mean temperature difference? Okay, if you look at here, okay, you have we have a parallel flow. So we start from T hot and then 1 and end with T hot 2. Okay, that you see the decrease in temperature of hot fluid and an increase in temperature of cold fluid, which is TC1 here increase to TC2. Okay, that is in a parallel flow. In the contour flow, okay, we can also make the same things. You see here the TH come at the highest temperature goes to TH2, and then TC at, okay, TC goes to this contour flow from point B to point A to TC1. Okay, so which one is log mean temperature difference? So it is okay. There is a different notation between the okay. So this one equal to delta T naught, and this one equal to delta T I. Sorry, is it correct? Yeah. So this one is again delta T O, and this one is delta T out. So sorry, okay. So delta TO is always referred to the hot fluid. Okay, and okay, instead of having that UA delta T, we can now replace the delta T with LMTD. Okay, and remember that this one only applicable for double pipe heat exchanger. So what if you have different type of heat exchanger? Okay, so if we have a different type of heat exchanger, then we use somehow a correction factor, okay, which is the F in this equation. Exactly the same equation, but we need to use F because F is basically how far it's deviate from double pipe. Okay, if it's really double pipe, so F equal to 1. If it's not double pipe, so it will deviate from 1. It will go. It will be less efficient. Okay, it will be less efficient. So how to calculate F? It's very simple. Somebody already built the graph. Okay, and in this graph, okay, for example, now I want to go for okay, this graph is used for 1 shell pass. Okay, this is 1 shell pass and even number of 2 passes. So it will be applicable for 1 shell pass, 2, for example, 2, 4, 6, 8 passes of tubes. Okay, and what we need to get is you need to find the correction factor, which is here. Okay. And to be able to get the correction factor, you need to find out Z. Okay, and you need to find out P. And the equation for Z and P is given in this graph. Okay, and then what is TI, TO? You can see it from this illustration. So this is the one we use for heat exchanger type other than double pipe. And then I only have 3 here. So first one here is one shell pass, an even number of tubes. This one is for cross flow with both fluid unmixed. Okay, and this is always happen in heat exchanger. In air conditioning. You use this graph. And lastly, we have cross flow with one fluid mix. Okay, cross flow with one fluid mix. So the same thing. So we need to find out F and use it in this equation. And to be able to get F in this equation, you need to find out Z and P. Exactly the same for the other type of heat exchanger. That's method number 2. And method number 3, sometimes you cannot use that one. Okay, you cannot use the LMTD method because, for example, you don't know the temperature. Okay, so we can use effectiveness NTU method. In this method, okay, there's some of the definition. Okay, so imagine you have heat exchanger like this one. So this is a contraflow heat exchanger. We have hot fluids come in at a temperature of TH in. So this is a hot coming in, and we have a T hot going out. Okay, and then there is a mass flow of hot. We have a CP data of the hot fluid. Similarly, we have a cold fluid coming in at temperature of TC in with a CP cold and at certain mass flow rate of M cold, and then it goes out as T cold out. So we have some definition. We need to know what is NTU, what is effectiveness factor, and what is the capacity ratio. If you have this kind of system, okay. So first of all, we have definition of Tmax, delta Tmax. Delta Tmax is the maximum possible temperature difference from the 4 points. So the highest is when the T hot come in, which is T hot in, THI in this case, and the lowest is when the cold temperature enters the heat exchanger. So delta Tmax then equal to this guy. Okay, THI means TCI. Then we have mass flow rate. Okay, what is the term? CH is defined as MH times CPH. Okay, that is what is the term? I don't remember. So it's basically the capacity of the stream, heat capacity of the stream. Okay, that's the MH. So for the and we have it for hot, and we have it for the cold one. Okay, that's the second definition. And there is a condition here. If CH is higher than CC, then we assign CH as Cmax. Okay, and CC as Cmin. Okay, that's the thing. So that's the condition. So conversely, if CC is higher than CH, then it is CC that is Cmax, and CH is Cmin. So that it will make sense later on. Okay, so we have the Q, key actual heat that is transferred. It is a CH, stream capacity of hot times the delta T hot, or it can also be as QC. Okay, CC times delta TC. This is actually equal to, if you expand it, MC CPC delta TC. Okay, so it's the same. Then we have a key maximum. Key maximum definition is that Cmin can be CC or can be CH depending on which one is lower. Okay, Then we have capacity ratio. So capacity ratio or capacity relative. So this one is basically C min divided by C max. And we have the effectiveness. The definition is Q actual divided by Q max. And lastly, we have the NTU, which is defined as AU over Siemens. Okay, A is the area of the heat exchanger, U is overall heat transfer coefficient, and C min is can be CH or can be CC. Okay. So another important thing is C relative equal to 0 when there is a phase change, condensation or evaporation. Okay. Based on this one, we know that the heat exchanger behavior is really depending on the flow arrangement. And the relationship between NTU, effectiveness factor, and capacity relative or capacity ratio can be shown graphically or can be described using some of the empirical equation. So how to do it? No worry about this graph. We'll give it to you. Okay, so you see here, I want to find NTU. So NTU, this is my guy. What I need is two. I need to find out effectiveness factor here and capacity ratio here. Okay, when I know two of the three, I'll be able to find out the third one. Okay, and then you have it for different type of heat exchanger. For example, the one on the left here is a cell and tube. One cell pass, 2, 4, 6, 8, and so on, tube passes. Okay, and then the one here in the middle is when you have n cell, so you have more than one shell, more than one passes of shell. So you have n shell passes and 2n, 4n, 6n, 8n, and so on for tube passes. So this is the graph for that kind of shell and tube heat exchanger. So for the cross flow heat exchanger, you have two here, unmixed. Okay, unmixed is here, and you have both stream, sorry, C min, C max, unmixed. Oh, and then at the bottom here we have both stream unmixed for cross flow. So we use which graph that is suitable for the problem. Okay, so based on this, you see, you might ask me, so the result won't be 100% the same if two guys doing the same problems. Oh yes, really depend on your estimation when you find out NTU in the graph. Okay, this is the one method using graphical. You can also use the equation, and then the equation here is given. You can find it in many heat transfer books, and it's really you have concentric tubes, counterflow. You have this equation to estimate epsilon. Epsilon here is effectiveness factor. This is equation for concentric tubes, but parallel flow. Then next we have shell and tubes. Okay, one shell pass and 2, 4, or 6 tubes passes. Okay, this is the equation for epsilon. Next for shell and tubes, but now you have n number of passes in the cell side, and 2n, 4n, 6n, 8n number of passes in the tube side. Next is for the cross flow, single pass, both fluid and mixed. Okay, this is more or less the illustration of the heat exchanger system. Next is the equation for cross flow single pass, both fluid and mixed. Then you have a cross flow single pass, C maximum mixed and C min unmixed, and finally cross flow single pass, C max unmixed and C min mixed. Okay, you can either use the graph, which I find much easier, or you can go with the equation if you're good with calculator. Yeah, the thing with calculation is that we actually don't know the NTU. So the equation here is you have to reverse the equation. It's quite challenging. Okay. Okay, next is, this is the last part. It is a heat exchanger optimization. Basically, optimization means how can I get more with the same resources, so with almost the same resources. So how can I optimize my heat exchanger? So if you want to optimize the heat exchanger, you look into this equation. Yeah. What can I do? Okay. First, if I want to maximize Q, I can increase the delta T. But delta T, you cannot do anything because it is the process objective. So we don't change it. U is also, you cannot change it. Huh? This is the function of the material, the function of the fluid, the function of the velocity, many. So what we can do is we can increase the A heat transfer area. And then how to do it is by the popular one is by using fin. Okay, you just add some fins outside of your heat exchanger. Okay, and then you've seen it a lot in your computer, in your laptop. If you open it, this is fins. Okay, this part is fins. You see here a lot of fins. Okay, fins. This is also fins. And the aim for this one is for increasing the Q, heat transfer. Okay, so what can I gain by putting more fins to my heat exchanger? Okay, so there are many types of fins. It can be integral with the base. Fin is integral with the base. So how to mount it? It can be welded, soldered, or even glued to the surface. Okay, it can be mechanically attached by embedding in groove or tension wound and so on. And you have different types. Okay, rectangular type here A. You have a triangular type, and you have parabolic types. Okay, and then it can be put in the shell, so in the inner part or in the outer part of the surface. Okay, so what advantage we can? So if you add fins to your heat exchanger, you can get, so Q total here. Q total is anything you get from the base plus anything you get from the fin. Okay, so anything you get from the fins is basically H, heat transfer coefficient, area of the fins, the efficiency of the fins, this is called as fin efficiency, and the delta T. Okay, from all of this one, okay, E of the fin, you can measure it, you can calculate it easily. You can easily calculate using geometry what will be the additional area of the fins, but how about the efficiency of the fins? Okay, people have developed one method. So this is the efficiency of the fins. Okay, it's really a function of the shape. Okay, a function of the shape, and you can see, you can determine the efficiency of the fins using graphic. Or for the fins with regular shape, we can use some equation. Okay, we can do some estimation. For example, here we get efficiency of the fin equal to 10. What is it? How to spell in English? 10H, 10 ml of ml, and then this is the definition of M, and you see the definition of dress. Px is perimeter of the fins equal to 2 times of the width plus 2 times of the thickness. Cross-section area AX equal to width times the thickness of the fins. And L is the effective length of the fin, K is thermal conductivity of the fin materials.